Yeah, what? Hä? What?
Papa Flammy's Advent Calendar.
Here.
Good morning, fellow mathematicians. Welcome back to another video. 10% of all mugs and cups over on Stemmers. Check it out. Got a new collection going. Became a bit creative, okay? Over the non-existent holidays, also 10 to 15% of everything over on my Teespring shop. Use code 42069. We're going to do an improvised session today, yet again. And the integral that we are going to deal with is this one right here. Someone on Instagram sent it to me. And I'm not certain if I can do this one because it looks extremely ugly, and I mean, I kind of have some idea how to approach it probably, but I'm not certain if I'm able to do it. We are just going to give it a shot and see how it's going to go. Other than that, don't forget to check out today's sponsor, The Rich, who are kind enough to sponsor yet another video here on this channel. More information at the end of the video, okay? But just as a matter of fact, they create absolutely amazing lifestyle products like those indestructible wallets and those absolutely good looking backpacks. I love it. More information at the end of the video, but now we are going to dive into the improvised session. Okay, so here was my initial idea. I wanted to parameterize this integral because, as a matter of fact, if we were to parameterize, for example, this integral as being one with respect to t, where we put a t up here, okay, then this one is I with respect to t, or just I with an index t, then if we were to differentiate this with respect to t using the Leibniz rule for integration, we would get rid of a logarithm term down here, okay, because this right here is basically an exponential function, and if we raise this to e to the ln of this power, we're going to drag a log of x down and get rid of one of those log of x's. Now that I'm thinking about it, it would be kind of weird to put a t up here. I mean, you can do so, but it's kind of pointless to put it right next to the phi, because we can just use it as an initial condition. Okay, so let's say we are dealing with this integral x to the t power minus 1 squared over log squared of x. Okay, so this is I with respect to t, and please notice that the integral I we are striving for, so the original one, I is nothing but our integral I, our parameterized integral with respect to phi. Okay, so yeah, let's use the Leibniz rule for integration and see where this is going to get us. I think this shall work to some extent at least. Okay, I mean, a substitution wouldn't do any good here. Meaning, what we are going to do is we are going to say, okay, what's the differential of I in t? That's obviously, okay, and the upper and lower bound are independent of our variable t, so we can drag the differential to the inside using the special case of the Leibniz rule for integration. This should work out. And then we're going to end up with an integral from 0 to 1, that's a good looking one, okay, we got 1 over log squared, where log is the natural log, obviously, as always on this channel. And x to the t power is nothing but, okay, let me see, this is e to the t log of x. And now you can see why I said, okay, we're going to get rid of a logarithm term here, because if we were to differentiate this, we're going to cancel this logarithm out. Okay, and negative 1, and this whole thing squared dx. And obviously, we are going to take the partial derivative of that with respect to t. After we do that, we are ending up with I prime with respect to t being, okay, let me write everything out from 0 to 1. 1 over log squared of x. Okay, differentiating this. We're going to, okay, yeah, kind of ugly. I believe we need to do another differentiation after that, because, yeah, okay, I think this is kind of ugly. Okay, we are going to drag the 2 down, okay, 2 times. We are going to preserve this factor right here just with 1 to the first power. So this right here was originally x to the t power minus 1. And then we are going to multiply it with the inner derivative. Negative 1 is going to vanish, and the inner derivative of this thing is Yeah, okay, so inner derivative of this thing is the derivative of that thing, giving us the log of x that we were seeking, but also we are going to multiply it with x to the t power dx. Okay, I mean, at least we got rid of one log of x, and now we got this ugly fucker. So integral from 0 to 1, 2 times. Okay. I mean, yeah, okay, let's see, this is x to the 2t power minus x to the t power divided by log of x dx. Okay, I'm not certain, maybe if we differentiate this we are going to get an extra logarithm that we don't need there, or that we don't want there overall. But we are just going to give it a shot, because if we were to differentiate those ones once again, we are going to get rid of the logarithm of x definitely. This is something that is going to happen, because this integral right here is nothing but e to the 2t log of x, and also we are going to have minus e to the t log of x. So if we were to differentiate this once more, meaning I double prime t, that's going to be, okay, 2 times the integer from 0 to 1 of. Now here's where the fun begins. If we were to differentiate those, just using the summation rule basically, that you are going to get all the time. So on the first one it's going to be 2 times log of x, times obviously this thing being preserved, x to the 2t power, minus and then log of x, times x to the t power divided by log of x. I mean, ultimately we got rid of the log of x now, which is good, leaving us with a pretty tame integral at least. I mean, this is way better than what we had before. So I double prime t is going to be, let's split this up. This is 4 times the integral from 0 to 1 of x to the 2t power dx, minus 2 times the integral from 0 to 1 of x to the t power dx. Okay, and this is what we need to integrate now with respect to x. I mean, this doesn't even look half bad at this point. Okay, now we need some arguing. We have found out the second derivative, meaning basically what we need to solve is a differential equation. We need initial values. Now let us take a look. So thing is, if you were to just integrate at first let us compute those. I'm terribly sorry about that. So if we can easily compute those, okay, let's take a step back. Computing those is going to leave us with x to the 2t minus 1 power over 2t minus 1. And then we're going to get negative 2x to the t plus 1 power over t plus 1, not minus 1. I'm terribly sorry. Sometimes I'm confusing differentiation and integration, and this is very bad. And also right here t plus 1 from 0 to 1. Okay. Plugging 1 into here is not bad. They are just going to vanish up here, and plugging 0 into here is going to make them vanish, meaning I double prime of t is going to be 4 times 1 over 2t plus 1 minus 2 times 1 over t plus 1. Okay, now we want to integrate all of this to get back to our I prime of t, and after that we need to integrate I prime of t yet again to land at our regular I. Thing is, if you just integrate this right here without any upper and lower bounds, you are going to end up with a constant. I'm not a fan of this approach. I love to make everything vanish using initial conditions, okay? Meaning we are still going to integrate everything with respect to t on both sides, but we are not just going to integrate it, we are going to integrate it with upper and lower bounds overall. That way we can get rid of the constant that is going to pop up when solving this differential equation, and then we can just integrate once more and hopefully land at the right answer. Now what do we need to integrate it with respect to? Let us find an upper bound. I mean, finding an upper bound is easy because we want to end up with a parameterized integral yet again, meaning we are going to integrate it with respect to t in the upper bound. But what about the lower bound? Is there a way to make I prime of t vanish with some lower bound. So with respect to t, yeah, that is easy. If we plug t being equal to 0 into here, we get x to the 0th power minus x to the 0th power is going to be 0, and integrating a definite integral over 0 is going to result in 0, making everything vanish. So the lower bound is going to be 0, and overall what we are going to end up with using the fundamental theorem of calculus is, since this right here is ddt of I prime of t, we are going to end up with I prime at t being equal to t, okay, just I of t. This is a parameterized integral that we want to have, exactly this one. And negative, that's the second part of the fundamental theorem of calculus, is going to be I at t being equal to 0, but we just now notice that it's going to vanish at t being equal to 0, meaning we're going to end up with I prime of t, which is just I prime t. What we have here. Okay, that's a lot of stuff. I just want to elaborate on this, and it helps me solving the thing actually big time. Now we are going to integrate those, and this is fairly easy actually. Okay, let's go ahead and get started. Let's write everything out. Meaning, so we have 4 times the integral from 0 to 1 of dt over 2t plus 1. Now let 2t plus 1 be equal to, I don't know, eta. Then that means that d eta over 2 is nothing but dt, leaving us overall with, okay, now we are going to get 4 over 2 is going to turn into 2. This is going to be from, yeah, I don't know, up and lower bounds, really don't care about that. We are going to plug this in a second. And other than that, oh yeah, since we have t right here as being the upper bound, really doesn't matter. Okay, we are going to get d eta over eta, leaving us with 2 times the log of eta, and this is 2 times the log of 2t plus 1 from 0 to t. At 0 it luckily vanishes. Log of 1 is 0, and leaving us this integral is 2 times log of 2t plus 1. Now what about the other one? We have 2 times the integral from 0 to t of dt over, what was it? T plus 1. Don't forget the negative sign, I'm going to put it here. Okay, we're going to get negative 2 times, and this is just log of t plus 1 from 0 to t, and by the same argumentations it's going to vanish, meaning we have I prime with respect to t being hence nothing but, oh, they both share a 2, meaning this is 2 times log of 2t plus 1 minus 2 times log of t plus 1. And now we are going to go through the same procedure again, that was easy, that we did here. We are going to integrate it respectively with upper and lower bounds, okay, and also with respect to t, and we are going to see what we are going to get. So our upper bound needs to be the golden ratio phi, because this is what our original integral looked like. We had phi up here where our t now is. So upper bound is going to be the golden ratio phi. Now what is the lower bound? Is there a way to make everything, yeah, obviously, once again 0. If we plug t being equal to 0 into here, we are going to get 1 minus 1. Hello, ghost chalkboard, okay, do your thing. 1 minus 1 is 0, making everything vanish yet again. Meaning the lower bound must be equal to 0. Yeah, that was easy. Meaning by the fundamental theorem of calculus, we are going to end up with, so this right here is ddt of I of t. The ddt and the dt is going to cancel out, so integrand differential basically. It's a consequence of the fundamental theorem of calculus. And this is going to give us I of t being equal to phi, which is nothing but our original I, minus I of t being equal to 0, but this right here is going to vanish. And this is going to leave us just with the integral I that we are seeking. So the only thing left is to actually integrate what we have here and see what we are going to get. Okay, let me see. So let us start with the first part. So 2 times the integral from 0 to phi of log of 2t plus 1 dt. Okay, we are going to introduce the substitution yet again, namely this one right here, because why the hell not? And meaning we're going to get 2 and 1/2 is going to cancel out, luckily. Then we have an integral from somewhere to somewhere, and this is going to be just the log of eta d eta, and that has a very nice antiderivative, meaning this is going to be eta times log of eta minus eta, but all of this plugged into 2t plus 1, leaving us with 2t plus 1 log of 2t plus 1, this is ugly, this is not nice, minus 2t plus 1 from 0 to far. Now, if we were to plug 0 into here, okay, 0 into here. Okay, then this right here is going to be, okay, this part is going to vanish, leaving us with negative 1. Seems like it's negative 1 on that side. And then negative, okay, far into here is going to give us 2 times far plus 1. Exactly, 2 times far plus 1 times the log of 2 far plus 1. And negative is positive, so plus 2 far plus 1. This and that is luckily going to cancel out, leaving us with this ugly fucker. Okay, let's continue with next one. 2 times the integral from 0 to far. I need to erase something such that I can fit everything on the next blackboard. Okay, this is going to be the log of, this was just t plus 1, right? dt. After doing a substitution, this is 2 times, okay, not a factor of 2 is going to cancel out, log of eta d eta, leaving us with, okay, this right here is going to be, okay, now we have a factor of 2 this time. So 2 times t plus 1 log of t plus 1 minus 2 times t plus 1, evaluated from 0 to far. Okay. Also, I shall not forget the negative sign that we are going to get in the process, meaning if we were to put a negative onto everything here, we are going to have a negative here and a positive sign here, leaving us overall with 0 into here. This right here is going to be 2. That's going to turn into negative 2, but all of this, okay, this right here is going to be just 2. That is going to cancel out completely because of the logarithm. And then we're going to have positive 2 times far plus 1 times the logarithm of far plus 1 and negative right here, leaving us overall with, okay, plugging far into here, negative 2 times far plus 1. Okay, and 2 and negative 2 is going to cancel out on this part, leaving us with what we have here. All we have to do now is add those two together, and then we are probably at a final answer that we can probably simplify, because Fire always does really cool things when adding it to 1 and the like, so I'm going to see in a second. So I erased everything, and this is what I have gathered up until now. And now we are going to see if all of this actually works out. So what I noticed is that 2 far and negative 2 far is going to cancel out while writing everything out. And what we are wait, no. Wait a second. From A to B. Yeah, what? Huh? What? Yeah, this is... I was already wondering this while writing everything out. It felt kind of weird to plug stuff in. I totally messed it up. I thought this up here is the lower bound A and this right here is B. So we need to switch the signs, I think. I don't know what... No. That was weird. So yeah, just changing the signs. And yeah, maybe you have noticed while I was writing out, I was already pondering it a little bit, because I thought it was kind of curious that I plugged stuff in weirdly from the upper and lower bounds. So I'm actually glad that I noticed, I think. So this right here is going to be a plus, but this really doesn't change anything on the cancellations, and this right here is a minus. So this right here is what we are left with. And now let's see if we can simplify something. Okay, let's write it out a bit. So far squared minus far minus 1 is equal to 0. Meaning we have that far squared is equal to far plus 1. No more sign mistakes, for frick's sake. Meaning what we have here is, okay, this right here is going to be the log of far squared, which is 2 times the log of far. Also, we can simplify this then. So this right here is also just far squared. Okay, what about 2 far plus 1? I mean, obviously, this argument right here is log of far plus 1. And this is log of far plus far squared. Okay. So this overall is, let me see for a second. I mean, I don't believe that there's any simplification that you can do immediately with that, because sadly we have a positive sign here. Even if you were to, so let's say we have far squared minus far is equal to 1, then adding far on both sides is going to give you, no, adding 2 far on, no, this is just what we ended up with originally, but we have far as a common factor, so we have log of far times far plus 1. But, oh, this is cool. I didn't know this identity before, but this is pretty cool. Since this right here is far squared, we are going to end up with log to the far to the third power, which is 3 log of far. This is cool. That's a cool identity. So 2 times far plus 1 is going to be far to the third power. So same spiel here. Okay, that's a huge mess that we're having here, but let's see if anything simplifies. So I is hence nothing but, okay, let me see. So we have far to the third power, 3 times far to the third power times log of far, minus 2, and what did we have? 2. So this is 4 times far squared times log of far. Okay, so we have log of far as a common factor, 3 far to the third power minus 4 far squared times log of far. Okay, that is kind of ugly. Can we do anything with that? Let me see for a second. Far to the third power. Okay, let me see. This is so. I mean, this right here is nearly that situation. So if we have 3 times far squared minus 3 times far minus 3, that's still equal to 0. Now we can multiply both sides by far, leaving us with 3 times far to the third power, then a squared here and a far here. Then we can add 3 far on both sides, leaving us with 3 far to the third power minus 3 far squared is equal to 3 far. Oh, that's a bunch of things. And then what we can do, we need negative 4 far squared here. We need to subtract far squared on both sides. Maybe that works. Negative 4 far squared is hence nothing but 3 far minus far squared. So this part right here is nothing but 3 minus far times far. Okay, that's something that we are having right now. And is there any other identity we can use? I mean, this is already a pretty nice answer if you ask me. This is the same as 3 minus far times log of far to the 5th power. This is pretty good. Okay, 3 minus far is going to be 6 over 2 minus 1 plus square root of 5 over 2. 5 plus... Okay. So this right here is negative 5 minus square root of 5 over 2. And multiplying this with the golden ratio is so 1 plus square root of 5 over 2. And let's see what this is going to result in. This is going to be 5, okay, over 4 obviously. And then we are going to get, this is going to give us negative, cool. Okay, so we got rid of this and this. Also we are going to have negative square root of 5. And also we are going to get, what's the last one that's missing? 5 times square root of 5. Oh my goodness! Okay, this is so cool. Okay, 5 times square root of 5 minus square root of 5 is going to be 4 times square root of 5 over 4, and this is square root of 5. Meaning, our integral I probably is square root of 5 times the logarithm of the golden ratio of 5. I think this is the answer because I did a mistake here, and even with that mistake I would have gotten a negative solution, so negative this value instead of a positive one. Then I would have just argued that it's an area because why the hell not, and it has to be positive, so I don't care. But yeah, this is cool. I hope this is it. If this were the answer, then this would be pretty cool. But before we actually end the video, like mentioned before, I would love to give a huge shout out to The Rich for sponsoring yet another video here on this channel. And I just love their products because they look really stylish. They come in so many different colors. Their newest gold collection and their Damascus collection. It looks absolutely amazing if you ask me. Still waiting for my new one, can't wait for it. And other than that, their backpacks, they are just so sleek, good looking, completely weatherproof, so much space in there. You can charge your phone using their phone chargers too, and all this good stuff. They got phone cases too. I just love The Rich, and I'm so glad that they decided to sponsor this channel in the first place. I think the most remarkable thing about their wallets is actually how sleek they are. So you can fit up to 12 cards into this. This right here is the carbon fibered wallet, Rich wallet, and also you can put your whole change on here. So you can put real solid change into here, but you can just take your cash and put it at the back side. So the paper cash, if you know what I mean. And you can actually get to your Rich wallet a money clip or this money strap that I'm having here. You can buy it extra, and it actually does a really good job keeping everything together that you really need during your daily life. And also, this thing changed my pocket situation immensely. In a normal case, I was running around with my old leather wallet, and if you're a real man like I was before getting the Rich wallet, now I'm a real mathematician, a real man. My leather wallet was approximately this big, and this really left a bulge in my pocket all the time. But this doesn't happen with the Rich wallet anymore. It's really slim, so really there's a big difference between a real wallet in terms of size. Okay, a real wallet is like this size, and it's just really good. I just love how it feels in my pocket, and you nearly can see that I'm having something in my pocket there. So yeah, that's really good. But also one thing is you're going to get a lifetime warranty on this wallet, meaning if it does break in some way, you can just send it back to Rich's Way. They are going to refund it completely for you because they actually promise you that this thing is never going to break. They swear on the durability of this tiny little thing. So if you want to try it out for yourself, make sure to check out the link at the top of the description, rich.com/papaflamme. With it, you are going to get worldwide free shipping, which is already pretty amazing in itself, plus 10% of your whole order. So try it out and support the channel this way. You can also use code papaflamme at checkout. And this basically concludes the video. I hope you did enjoy this improvised session. I'm just now noticing that one of my sound absorbers actually got unstuck from the wall, which is kind of weird, but now I fixed it, and yeah, I for myself really enjoyed this one, and I hope that the answer is correct. That was quite exhausting. This involved a lot of integration. It's an integral after all, but I'm glad I did it. That was a good improvised session, I think. Yeah, other than that, thank you guys for watching. Check out the advent calendar over on STEM merch too, and also my Teespring shop, and up until the next video, I wish you guys a flammable day. Ciao!